Okay, today we're going to continue section 5.4. I've got some notes up on the board. I'm going to give you a minute to copy those down. Okay, I'm going to talk through some of this stuff. The first thing you see is the fundamental theorem of calculus. We've been using it a lot. I think you probably feel fine with it. That's this part. That's the normal part that we've been dealing with. Then it says an alternate part of fundamental theorem of calculus. You may remember we had an alternate definition of derivative, so it's kind of like that. It says, here's an alternate part of fundamental theorem of calculus. As long as f is continuous on this closed interval, then capital F of x, which is the antiderivative, has a derivative. So I just said capital F has a derivative on every point. And the derivative, okay, so see how that's the derivative of capital F. So we're taking the derivative of the antiderivative ends up just being lowercase f. Now hopefully this makes sense, because doesn't this operation, which is derivative, and this operation, which is antiderivative, don't they kind of cancel each other out? Just like a square and a square root would cancel each other out. So hopefully this makes sense, that the derivative of the antiderivative, these two functions together are just going to kind of cancel each other out, and you end up with just f. Now you notice how I've got some different letters in here. We're going to talk about that. So why does this make sense? Why does this alternate part of fundamental theorem of calculus make sense? It says we're taking the derivative of an antiderivative. I've stressed that already, so it makes sense those cancel out. Now, did you guys notice that there's a little a here and an x here? So a is a constant and x is just x. It's your variable. So does it matter what a is? Could a be 0 or 5 or 10 or -3? Why? What happened to the a here in the f of x? Where did it go? Here's why it doesn't matter. If you look here, we have capital F of b minus capital F of a. That's our antiderivative. Now what we're seeing is we're taking the derivative of that, right? Because we're taking the derivative of the antiderivative. Well here, since in this case, the b is an x. See how there's an x on top right there. So it would be f of x minus f of a. And when we take the derivative of that whole thing, the derivative of capital F of x is lowercase of f. What would the derivative of capital F of a be? Isn't capital F of a just a constant? So the derivative of a constant would be 0. So no matter what that a was, whether it was 0, 5, 7, -2, when you take the derivative of that constant, it's going to go away. So it does not matter what this a is right here. It can be 5, 0, 7. The derivative of that is going to go away. So no matter what this a is, this part still remains the same. Now you might also be wondering, okay, why is there a t here? Why is there a t here and an x here? Does that matter? Really, it doesn't. What matters is that we have this variable right here on top, which is the x, okay? This x right here can't really be the same as this variable. So we just call this t a dummy variable, and what we end up doing, I'm going to use this terminology later, is we take this x and we kind of dump it in. We decide, okay, we're going to dump in the x into whatever variable is there. It doesn't matter if it's an RDR or a theta d theta. So that t isn't going to end up making a difference, and you'll see that hopefully as we do some examples. All right, so we've got the fundamental theorem of calculus. I'm going to erase all this mess I wrote on the board. And it says, once again, that the derivative of an antiderivative ends up just being the function. that was there. What did I call that? The integrand that I said I wouldn't use much? All right, let's move on then. So here's what I just had written up there. Right, that's the thing that you just copied down. So we have our first example. It says, find the derivative of the integral from 0 to 1 of the square root of 1 minus t squared dt. You can see we have dummy variables in there. There's the t and the dt. They're dummy variables. And it's asking us to take the derivative of the antiderivative. So aren't those really just going to kind of cancel each other out? So what we do is we take this x and we dump it in to our t. Because remember, see how here we have a t, but here we have an x? So when we pour that x into the t, we just get f of x. And so that would be the square root of 1 minus, instead of using a t, we're using x squared. Let me write that so you can see it better. So this ends up just being 1 minus x squared. The derivative, the antiderivative canceled each other out, and so we end up with just our function or our integrand. I'm pausing so you can talk or ask questions of each other. Does that make sense? Okay, the next question. It's really the same question. I've just worded it a little different. Okay, this says find dy dx. Isn't that telling you to find the derivative? If y equals this. So if it's asking you to find dy dx and this is y, isn't it really saying find the derivative of this integral? See, if it's saying find the derivative of y and this is y, then we want to actually find the derivative of this function. So once again, see how you have derivative, antiderivative. This, just like this 0 didn't matter here, this negative pi isn't going to matter here. We take our x, we dump it in, and so we end up with just cosine of x. I mean, actually, math-wise, these are incredible. They're really easy. The derivative of an antiderivative is just the function. Bam, you're there. You write your function in terms of x, and you're done. Let's see what else we're going to take a look at. Surely it's not always this easy. Okay. So now, what if the x, the one that's on the top, the one that's the upper limit, the b, what if the x was actually a function, an f of x? What would we need to do to take the derivative of an antiderivative function with a function inside? So the antiderivative is a function. That's the integral part. But then instead of an a and a b, our b is a function. Doesn't this sound like a function inside of a function? So how do we take the derivative of a function inside a function? You got it, chain rule. So we're going to need chain rule. Remember that chain rule is the derivative of the outside, which the outside function is technically the integral here, times the derivative of the inside. And the inside function on these examples is the upper limit, or the b. Pause a minute. Okay, so here's our first example. It's asking us to take the derivative of the integral 1 to x squared of cosine of t dt. So you can see we're taking the derivative of an integral. Those two are going to cancel each other out. But we have a function inside of our integral function. So sure, these two cancel each other out. So we're going to take this x squared and dump it in. Oh, we're not just dumping in an x, we're dumping in an x squared. So that's cosine of x squared. I dumped my cosine in. Now, I took the derivative of my integral. I took that derivative. But now I need to take it times the derivative of the inner function, and that is 2x. And so I would want to write this instead just as 2x cosine of x squared. I just reordered it. So I still dumped my x in. I did, although instead of dumping in an x, it was an x squared. And because I had a function inside of my function, I had to use chain rule. All right. Questions there? I'm not here to answer that. Hopefully someone can. Let's look at another one. This one is worded like that second one was. It's just saying, find dy dx if y is the integral of, fun function, the integral of sine to the fourth of t dt from 2 to 1 over x. This is a 1 over x here. So you see how we have a function inside of our integral function. And it's asking us to take the derivative of it, isn't it? So it's saying find the derivative of this function. So we're taking the derivative of an integral. So that means that this function and this function are going to cancel each other out. So we drop this guy in for x, and that would be sine to the fourth of, let's see, 1 over x. I dropped my function in, and now I'm going to take it times, I took the derivative of my integral function. Now I need to take it times the derivative of the inside, and the derivative of 1 over x is negative 1 over x squared. So I suppose I could write this as negative sine to the fourth of 1 over x divided by x squared, and that would be an okay answer. All right, visit if you need to. Answer each other's questions. Okay. Now, let's think back. We have some rules for integration. Do you remember how if we switch the a and the b, the spots where the a and the b are, we have to make that negative? So, if that happens, what if instead the x is on the bottom instead of on the top? See how this x is here and we have the b up here? Wouldn't that mean that if I put the b on the bottom and the x on the top, the x on the top, that I have to do the opposite of it? See how when you switch the place of the lower and the upper limit, you have to change the sign. That's going to happen on this next example, okay? So on this next example, you look, they're asking us to find the derivative, but look, our a is on the top instead of the bottom. That's no good. And so what we're going to do is we're going to think about y instead as the opposite of the integral from 5 to x of 3t sine of t dt. Okay, so all I did was I switched where my a and my b were, which means I had to change my sign. Now, it's asking me to take the derivative of this integral, the derivative of an antiderivative. So dy dx then is going to be, I'm going to dump my x in. Oh, did you notice there's 2 places to dump my x in? So when I dump my x in, I have 3x sine of x, and I have this negative out in front. I didn't have to use chain rule that time, did I? There was just a plain x on the top. All right, so there's the answer to that one. Let's look at one more. Doesn't want to get any bigger, so I'll read this for you. It says, find dy dx if y equals the integral from 2x to x squared. You have a 2x on the bottom and an x squared on the top of 1 over 2 plus e to the t dt. All right, everybody got that? Integral from 2x to x squared of 1 over 2 plus e to the t dt. Oh, holy cow. We don't have an a or a b. You notice how we have a function as our lower limit and we have a function as our upper limit. Okay, so what's going to happen here? We don't have a constant anywhere. I want to come over here to the side, so pause your notes there for a minute and come over here and listen to me. If I had the integral from something like, if I had the integral from something like, well, I'll just choose a to b. Wouldn't that end up being the integral from 0 to b, all right, the integral from 0 to b minus the integral from 0 to a. Think about that for a second. All right, if that's not making sense, I'm going to try with numbers. Let me try with numbers here. Let's say I had the integral from, say, 3 to 10. Okay, and there's going to be a reason I'm using 0. Give me just a second. So the integral from 3 to 10, that would be the integral from 0 to 10. Isn't that too much? 0 to 10 is too much. So how about if we take away the integral from 0 to 3? Okay, did that make sense? The reason that I'm doing this is because I'm going to try to make it so where I have zeros on the top and the bottom here. I'm going to try to make it so where I have zeros in one place or the other. I just need to have some kind of constant there. All right, so are we okay with this over here in the black and the red? Okay. If that's okay, then I'm going to erase this. And I'm going to show you what I'm going to do over here. I'm going to rewrite this integral. Instead of going from 2x to x squared, I'm going to rewrite this as the integral from 0 to x squared of this function, 1 over 2 plus e to the t dt, minus the integral from 0 to 2x of this function. Okay? So I'm using that same idea I did last time. So hopefully you're okay with this. And now look, oh great, I have a constant here and a function on top. I have a constant here and a function on top. Constant here, function on top. So now I can go ahead and take the derivative of both of those integrals. So when I find dy dx, the first thing I'm going to do is take the derivative of this integral, okay, which means I dump this function in. I'm going to need chain rule here, so I'm taking the derivative of this integral. So it would be 1 over 2 plus e to the, what am I dumping in, x squared. And don't I have to take that times 2x because I'm using chain rule. Now, minus, and now when I'm taking the derivative of this integral, I'm going to dump in my 2x. So I have 1 over 2 plus e to the 2x. And now I'm using chain rule, so I have to take it times 2. So could I rewrite this a little nicer and say that that is 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x? And that would be my final answer. Okay? So look at that for a second. Do you notice that our final answer is really just x squared plugged in, which is kind of like our b, minus our 2x plugged in, which is kind of like our a. Isn't that really kind of like doing b minus a? So I'm telling you this because ultimately you guys may not have to write this step as long as you understand really technically that's what rule we're using, but we can still do the top minus the bottom. Remember today, we are taking the derivative of all of these functions. We're taking the derivative of an integral or the derivative of an antiderivative. So we're not actually taking the antiderivative, are we? Because we're taking the derivative of the antiderivative and those two cancel each other out. There's your assignment. It's section 5-4, number 37 through 46. I'd like for you guys to try very hard. I'd like for you to help each other. Be good to the sub, behave, tell her to have a nice day when you leave, and then I will be back tomorrow and we'll go over any lingering questions you have. Have an awesome day.